research at Florence Berkeley National Lab. And today I'm going to bring you a presentation about an investigation of Redshift-Space distortion and Alcok-Pacynski test degeneracy. So what is this presentation about? It's about the universe. Okay, so this is a map taken by satellite WMAP. It's actually a cosmic microwave background picture, and it's a part of our universe. So this is a project that studies the universe. So scientifically, we call it the cosmology project. So what is cosmology? Cosmology is a subject that studies the evolution of the entire universe. Like the Big Bang theory says, that the universe was originally a singularity, a small point, and suddenly was a Big Bang. And after nearly 14 billion years of evolution, the universe has reached a stage we can see today. And unlike astronomy or astrophysics, cosmology really focuses on the entire universe. And it's actually physics-oriented. The two columns that support cosmology is general relativity and statistical mechanics. So this is a cosmology project. But what exactly does it study in detail? It studied dark energy. So I believe most of you have heard of notions like dark matter and dark energy, but what exactly is dark energy? So let me give you an experiment first. Here is my batch. Here, oh, there's a pen. So it's a pen. What if I release it? It will drop. It will drop to the table. And why? It says gravity. So gravity is actually something that pulls things together. Okay? And think of another thing, like water fountain. No matter how fast the water is burning out from the pipes, it will eventually reach the highest point, and it's due to gravity. Gravity pulls things. So, naturally, physicists think that even though there was a big bang, okay, the things are moving apart from each other. But if gravity is the dominant power in this universe, then the speed of this moving apart is actually slowing down. So there was a negative acceleration. Now, physicists thought that this is the model we have. But unfortunately, back in 1998, two teams in cosmology community discovered that the acceleration of the universe, the expansion of the universe, is actually accelerating, which means there's something out there in space that's pushing things apart. It's anti-gravity. It's pushing things apart. It's actually making the expansion of the universe accelerate. So, we don't know what it is, so we call it dark energy. Nowadays, we know that around 68% of the universe is made up of dark energy, and the rest is matter. I'm not going to elaborate on the difference between dark matter and ordinary matter. But I think you should know that the difference between matter and dark energy is that matter can generate gravitational field, will pull themselves together. And dark energy is actually pushing them away from each other. So they're competing with each other. So, because this discovery of expansion of the universe is actually very, very stunning, in 2011, the Nobel Prize was awarded to Professor Reed, Professor Schmidt, and of course Professor Commuter in our school. Okay? So now, this is a project about cosmology. And now, let me ask you a question here. How do we know that 68% of the universe is made up of dark energy? How do we know the number 68? Of course, we make observations. We're collecting data. So back in the days, people make a timeline for the experimental observations of dark energy parameters. So here's the table for the timeline. We're now at stage 3. Okay, the difference between different stages here is that we're using better instruments. But we're doing the same thing, we're observing the sky, but with larger area. So we can collect more data. Okay, so now we're at stage 3. But let me ask you another question here. How do we know that the surveys, the telescopes and the satellites in the future, stage 4, are better than the telescopes and satellites we use now in stage 3? How do we know that? And how well can we expect that the data from the future can help us to constrain the dark energy parameter, like 68%? And how well can they help us to select the correct cosmological model? Maybe you say that just wait for the data coming out, but that's not correct. Why? Because if we don't know the satellite or the surveys are better, then why do we initiate the survey? Why do we send the satellites up into the space? So that's the logic. The logic here is we have some theoretical method that can help us to predict, to forecast the constraining power of these methods, these telescopes and satellites. So these years, people have used some very cutting-edge theories to predict the errors. And now in this project, we're using two different methods to do that. The first one is RSD, Redshift-Space Distortion, and the other one is AP test. Especially, we will explore the degeneracy. So we'll forecast the errors. Now, the more important thing here is we want to find what is the best way to doing these surveys. What is the best way of constraining the parameters? We will give some feedback to surveys based on our analysis. So the two general methods we use are RSD and AP test, especially the degeneracy. Okay, I'm going to talk about this method later, but first, why is it important to study dark energy? Why is it important to know exact values of dark energy parameters? Because we can understand the past and predict the future. Think about it, we have the exact values of dark energy, and then we can know whether the universe will continue to expand forever, or there will be a big crunch where the universe will collapse someday. Okay, so that's one of the points. And the second one here is that because dark energy has become one of the central topics in modern physics. Okay, so it's closely related to string theory, the quantum field theory, and all those theories. And who knows in the future, maybe we can use dark energy to solve our energy crisis. Who knows? But this is a cover of Science magazine back in 1998. So they rank the discovery of the accelerated universe as the scientific breakthrough of the year. So it's the top discovery among all scientific discoveries that year. Now, as the background, we're moving on to my research. So DASI. DASI is a stage 4 survey supported by Lawrence Berkeley Lab and the Department of Energy. So here is what we found. AP test is able to constrain the dark energy parameters by constraining a parameter called DAH. And RSD is able to constrain the dark energy parameters by constraining a parameter called F sigma 8. And here are the results. A redshift here means that if a galaxy has higher redshift, it is farther away from us. So the Mayo telescope used by DASI is just scanning different layers of redshifts, and it's taking data from different layers and then analyzing. So here are the results we forecast. Let me give you a more intuitive. Here, this is a constraint of F sigma 8. Well, you can see that at low redshift and high redshift here, the constraints are not very good. Although here we're reaching almost 1% error. That's percentage error. So we're thinking that any way we can improve this constraint, so we work hard. It's another table, but I will show you a more intuitive one. The red line here represents the improved constraint. You can see that when the arrow goes down, the constraint goes up. So we have better constraint here. But I'll give you another way to show this comparison. Here are arrow ellipses. If the errors are smaller, then the area of this ellipses are smaller. On the left side here represents the original constraint. And on the right there, that represents the improved constraint. It's very clear that the error on the right is actually smaller. So the constraint is actually better. But that's not the end of the story. We're using the degeneracy, you see. We have correlation coefficient here, which means these two methods are actually correlated. We want to explore the correlation here. So we're actually using this. What is it? Well, if we don't have the degeneracy, for example, the constraint of F sigma A will become the center from here to the very edge here. But now if we have the degeneracy, the arrow becomes from the center to this intersection. So, this is a comparison table here. You see that the degenerate data here is actually representing smaller errors and better constraint. A more intuitive graph here. See, the green line now represents the degenerate constraint. You can see that we're actually reaching lower than 1% error. And it's actually a very flat curve here, this part. We're doing a very good job here. So that's how we actually try to constrain dark energy parameters by combining these two methods. And actually we will try to use these two methods to constrain more surveys, to study more surveys. And we may incorporate more techniques other than RSD and AP test, like DOA or something like that. So, more importantly, we're still trying to find what is the best way to constrain the parameters. What is the best way to do those surveys? Okay? So, here are the references, and my supervisor is Uros Seljak, the director of BCCD, and also working with Dr. Morrison and LBL and UCB and special thanks to serve. Any questions? Yeah.
So is the reason why you're studying the degeneracy between the Alcok-Pacynski test and Redshift distortion just because those are the two main tests that DESI is